Alrighty, capacitors, baby. So this is the basic definition of capacitance. That's charge in coulombs. That's the potential in volts. In volts, and this is potential as well, right? That's going to be in volts. Right? And then this is our capacitance. That's in farads. Right? Remember a microfarad? Microfarad is 10 to the minus 6th. Picofarad is 10 to the minus 12th, right? Okay. And then this is capacitors in parallel. Actually, they just add up. Okay. It's just like you're hooking batteries in parallel. They work the same way as batteries, right? So, that's parallel, right? You could imagine that I could draw this, right? You're just basically, it's like having more capacitors. They just add up. And then in series, because the voltage splits across them, you actually store less, right? So series is, we don't joke about that. We're series. Okay, there we go, right? This is the formula for a capacitor. Say you've got the area of these plates, right? Is the A. D is this distance here. Right? And then this is the permittivity, right? If it's epsilon naught, it's what? It's like 8.85 times 10 to the minus 12th or something like that, right? Okay. But is that what it is? I don't know. I forget. You can look it up. But oftentimes the permittivity is more than that. So it's some dielectric constant times the fundamental permittivity of just a vacuum. Okay. So that's what's going on there. This is like the engineering formula for a capacitor, right? So this is, again, farads. This is capacitance, capacitance. That's capacitance, right? This is the energy stored in a capacitor. So again, that's our capacitance in farads. And then this is energy in joules, right? And then all of these things are the decay, right? So we've got the initial decay. So we've got, let's see, right? This could be the charge on it. This could be the current flowing off of it. It could be the voltage. And the notion is that it goes like that, right? That it's that I, or the voltage across the capacitor, or the charge on the capacitor, is equal to some initial quantity, right? E to the minus time divided by the time constant, right? Okay, I think we did a lab on that, right? They all drop away. So this is exponential decay. Exponential decay, right? And you can, by the way, if you charge the circuit, it's going to look like this. I've seen problems that are like that, where it just goes like that, and it approaches that voltage like that. And then it would just be I naught, for example, 1 minus e to the minus time over tau. Whoops, parentheses like that. So if they give you something like that, just do a 1 minus. I can't think of anything else. So this is of course the resistance. So an RC circuit would look like this. You've got a capacitor. We've got a resistor. I'm going to draw a communist resistor here, right? And then here we've got a switch, like that. And this capacitor is all charged up. Here's our R, here's our capacitor, right? When we close that switch, it's going to go boom, like that, right? Yeah. I think that's all of capacitance.